Very good afternoon to all my students, teachers, and other participants. It's really a privilege to speak about this topic called Scientific Opportunities for Indian Astronauts on Lunar Surface. I would like to first thank Space Program Office, IIRS-ISRO, particularly Dr. T.P. Das for organizing this particular event. And it's really a very good event to interact with all of you. Thank you so much. So basically, astronauts can do wide variety of things on the surface of the moon, but I will be only concentrating on geological and geophysical perspective today. Why astronauts? We can also send rovers, which is usually done in the last few tens of years. But astronauts have an advantage because he can carry out multiple scientific tasks on the lunar surface more efficiently in a short period of time that cannot be easily done by robots. So this is the major advantage why astronauts have to move to the lunar surface. Science is a major driver for lunar crewed missions. So when an astronaut goes to moon, he or she has to have the scientific understanding with a view to understand the moon. The main outstanding questions is how did moon form and evolve to its present state? This is the fundamental scientific questions that drives the lunar science. To address this question, I break this topic into a number of subtopics. For example, giant impact on moon formation. This is the beginning of the moon. Then magma of ocean. This is also an important science topic that astronauts have to deal with. The third, late heavy bombardment, volcanism, tectonism, then meteorite impacts, medium to small scale impacts, then landslides, debris flows. Then of course, the regolith, which is called lunar soil. How does lunar soil form? What is its importance? Because we are dealing with the lunar regolith first. Then another topic called the seismicity, the origin of moonquakes. It's very important because it helps to image the interior of the moon. The internal structure of the moon is also very important, which has to be studied by the astronauts. Then magnetic field. What is the nature of magnetic field of the moon? And of course, natural resources also very important. Is there anything there on the moon to exploit? Then finally, we have to habitate the moon for long term. What do we do there? So these are the fundamental things that I'm going to deal with today. So if you look at our inner solar system, planets, the moon is the smallest body, right? So the Earth is the largest one. If you look at the geological activity, Earth is a very active planet in the solar system because the inner solar system, because of its large, huge size. So the internal heat engine is very active. So the surface also very young. On the other hand, moon is a very small body, so it's lost all its heat very early. So it's frozen, the surface is frozen very long ago. So moon surface hold the geological history of the first 1 billion year of the solar system. So this is the most attractive point why we are exploring moon. Because by understanding moon, we can understand the first 1 billion year history of Earth, Venus, and Mars, and so on. So this is the very attractive point for lunar exploration. So because we have to do geology and geophysics of the moon, we have to deal with the rocks materials. For example, on Earth, here you see the layers of rocks, which provides a lot of insight into how the planet formed, how it evolved over a period of time. For example, you deal with igneous rocks, sedimentary rocks, and metamorphic rocks. Similarly, we also look at similar type of rocks on the moon and study the geology. For example, another example, for example, on Earth, geologists go and visit the rocks and look at the structures that are found inside the rock and try to understand how Earth behaved in the past. So the visiting the rocks exposures is very important for Moon. That's why astronauts have to go to the Moon and look at the rocks. That's a very important task. Also volcanism, for example, here there's a lava flows which are examined by geologists. Similarly, the astronauts also have to visit the volcanic lava flows on the Moon and understand how volcanism occurred on the Moon. So on the other hand, geophysics looks into the interior of the Moon, for example, the crust, mantle, and core. What is the size of the inner core, outer core, mantle? So these are has to be estimated by the geophysical studies. So that's why it's very important. So in the last 50 years, there are several missions went to the surface of the Moon, landed, both rovers as well as human beings. For example, astronauts, for example, from Apollo missions, they visited several parts of the Moon. Similarly, in the future also several rover and human missions going to visit the lunar surface, particularly the polar region of the Moon. So what are the scientific interesting things to be explored? We will come in the next slides. So look at how the lunar surface provides lots of opportunity. For example, you have rocks and soil on the surface of Moon here, and you can also install the geophysical instruments that will be studying the interior of the Moon. So it's very beautiful. It's like Earth, you can do geological field work. Like you look at the landscapes of the Moon, you can see mountains and you can see plains and impact craters. Lots of materials came of that impact craters. You can look at the volcanic lava flow and rivers, volcanic lava flow. These things can be studied by astronauts. They need not walk. You can use rovers. Some vehicles also you can use and you can travel fastly. So several things can be done on the surface of the Moon. Here is another example. You can see how an astronaut explored the surface of the Moon, and he used a moving roving vehicle, and they looked at the rock surface, collected the samples to study the geology of it. Here you look at the soil materials that were excavated by the astronauts for sampling. So now we'll come back to the science. What is the science these astronauts have to understand? The main and foremost topic is the origin of Earth and Moon system. So how did Earth and Moon system form? That's a very important scientific question. Did they form from a single source of planet elements? Did they occur at the same time from the same set of planetesimals? Or was Moon captured by Earth? Or did Moon form from a single or multiple giant impacts of large bodies colliding onto proto-Earth? So this is what called giant impact hypothesis. So the giant impact hypothesis can also be tested by the astronauts by bringing huge amount of samples from a particular places which provide answer to these questions. Let us look at what is this giant impact hypothesis. So the giant impact hypothesis, two bodies collides, one smaller body, a smaller planet collide onto a large planet. So they collide each other. This collision produced a huge amount of debris materials out of the large body and also smaller body. Then from the disk of debris, Moon finally formed, and some amount of debris materials goes back to Earth and accretes to Earth. Finally, you have Earth-Moon system. So this is one of the most attractive hypotheses today many scientists are exploring. And this can be achieved by two different ways. For example, you collide impact one large body and smaller body. On the other hand, you can also collide equal sized body. So this collision produces a huge amount of debris materials comes out of these planets, and finally it produces a disk around it. And same way you can also produce the impact between two equal sized bodies. So the moments you produce a debris around by these giant impacts, so the huge amount of these debris materials goes back to and accrete back to Earth because of its gravitational influence. And whatever materials left out beyond the gravity field of Earth, they produce more amount of materials, they comes together and form moon. So how can we understand this? For example, if you bring a huge amount of rock materials from the moon, and you also study the rock samples from Earth, if you compare them, the isotopic systematics of these two materials, it shows that there are some relations. For example, the isotopic composition of the moon and the Earth looks very similar in nature. Similarly, there are several other isotopes can be studied. So this is one of the goal. When astronauts brings huge amount of samples of different diverse ages, they're going to address this giant impact hypothesis in a big way. And second one is the two sides of the moon. For example, the near side looks very different from the far side of the moon. So look, the near side has the dark patches called Murray basaltic lava flows. They are more in quantities. Whereas if you look at the far side, you only found few patches of Murray deposits. On the other hand, the far side has a huge amount of highland materials called anorthositic materials, which is slightly relatively less on the near side of the moon. Also, the crystal thickness also differs from near side and far side. So why these two sides of the moon looks different? This is very fundamental questions. Astronauts can look into it. Yeah, let's begin with the magma oceans. Once the moon accretes, it's a huge amount of impact heat energy and also radiogenic isotope also release a huge amount of short-lived isotopes. They molten the moon. So the upper half of the moon was completely molten and it produced magma oceans. So this magma ocean is almost a thickness of 1,000 kilometers. Then what happens to these magma oceans? So there are crystallization of minerals occurs. For example, olivine, pyroxene are the minerals which crystallize first, and they're very denser than the remaining liquids. So they settle on bottom of the magma ocean and they produce the mantle. At the same time, from the magma ocean, the mineral called plagioclase, which is basically calcium, aluminum silicate, this is the very lighter minerals when compared to the magma. So they are floating to the surface of the magma. They become the crust of the moon. So this is the anorthositic crust is the product of the magma ocean hypothesis. The mantle, which is olivine pyroxene, forms the mantle part of the moon. And the residual liquid is highly enriched in potassium, Re, and phosphorus. That layer called creep, which occurs between crust and mantle, is a very highly radiogenic mineral materials. So this is so can we sample all these materials? Yes, that's the purpose of astronauts go and bring samples of crust and mantle materials, gives lots of idea about the magma ocean. This magma ocean formed about 4,480 million years ago. And it took about 200 million years to completely crystallize. So this is based on the samples brought from the moon. Otherwise, we will never know how this has happened. Therefore, in order to further understanding the entire crystallization history of the magma ocean, we need to bring some more samples. That's very important. Again, when the astronauts land on the lunar surface, they will be finding millions of craters on the surface of the moon. You look at this topographic map of the moon, contains wide range of craters of diverse sizes and shapes. So there are full of craters. So this is what you find. If you land anywhere on the moon, you will certainly going to see an impact crater. So we are going to understand, the astronauts going to understand the impact processes on the moon. For example, look at between about 4 billion years ago, the impact flux was very high on the surface of the moon. It produced very, very large size impact craters on the moon. Look at the Mercury. Mercury surface also have many craters comparable in size and quantity that of moon. So this Mercury surface also, the craters there also looks very similar to the moon in terms of the population density. Therefore, the late heavy bombardment that occurred on the moon between 4 and 3.7 billion years ago also occurred on the surface of Mercury and also the Mars. Particularly, you look at the southern hemisphere of Mars, you find similar population of Mars. Therefore, what I'm saying is the impact craters that produced lunar surface, they also similarly they produced craters on Mercury, also Mars, probably Venus as well. So there are asteroids which are sitting in the main belt asteroids. So they all come together, they traveled across the inner solar system, they butchered all the planetary surfaces. So it's a huge process. It's not a small restricted to the moon. Therefore, by understanding the impact history of the moon, we will be understanding the whole inner system, solar system dynamics, particularly how the meteorites, actually how the asteroids traveled across the solar system. So this is one particular theoretical model called Nice family of models, where the large giant planets migrated in the first just 200 or 300 million years. What happened? The Jupiter, Saturn all migrated from the inner part to the outer part. During this migration, huge amount of the asteroids all scattered around the solar system. They impacted Moon, Mars, Venus, and so on. So therefore, this by understanding a lunar history, we will be testing some of these models like giant planet migrations along with other theoretical models. Therefore, the giant planet migration produced huge amount of impact flux into the moon, which decreased over a period of time. But if you look at this diagram, you will find that between 3.5 billion years to 1 billion years, you find there is no data. So this data has to be brought down. We have to bring lots of samples from different parts of the moon to fill this data gap. Then only this flux model will be accurate. So this is one of the objective for the Indian astronauts. Look at this, the largest impact basins on the moon called South Pole Aitken Basin. This is the largest one. This particular basin produced a huge amount of ejecta deposits, which is usually coming out of the impact, thrown out. This SPA ejecta is also sampled by Chandrayaan-3. Therefore, if we go and land in the SPA ejecta, we bring the samples back to Earth, we can understand this South Pole Aitken Basin impact process much better. We can also date this event, and we can also get the materials which are coming from crust and mantle depths. So that's also very important for understanding magma oceans. The other crater at the basin is called Imbrium basins. The Apollo samples also contain some of the ejecta materials came from these Imbrium basins. The dating of those samples assigned the age of the Imbrium to be 3.94 billion years. Similarly, the Copernicus crater was also dated to be 790 million years. So these samples coming from different parts of the craters, for example, the Oriental Basin, which is one of the largest basin on the moon, we don't know the absolute age of this impact event. So we can bring some samples from the Oriental Basin interior. So that also gives very precisely the impact timing of this particular basin. The other one, Tycho. The Tycho crater is just 85 kilometer diameter, which is somewhere here. Even you can see this crater with your binocular, or even naked eye, you can see this crater also produced about just 100 million years ago. So this Tycho also can be sampled. For example, Tycho also thrown huge amount of materials which traveled to Chandrayaan-2 and 3 landing sites. Therefore, if we bring any samples from this landing site, possibly we can bring the ejecta of Tycho back to Earth. For example, the landings like Chandrayaan-2, Chandrayaan-3 somewhere far away. The materials also there in this landing site contains ejecta material from different craters surrounded by them. Therefore, whatever sample that you are getting from the landing site is a mixture of ejecta materials that comes from thousands of craters. So if you take a 1 kg of sample, definitely that sample has the materials from thousands of craters across the moon. See, for example, here, the Chandrayaan-2 and 3 sites are surrounded by thousands of craters. All of them must have supplied some amount of materials to this landing site. So therefore, this is very important. Look at this Chandrayaan-3 landing site is surrounded by even smaller size craters. they also supplied materials to the landing site. So you can now understand how the inhomogeneous is the materials that you find from the landing site. This is at the Chandrayaan-3 landing site. You can find small centimeter size craters. They also give through materials. They also contributes to the sampling. So finally, at the landing site, either it's astronauts or any lander or rover, basically they have to deal with the lunar soil called lunar regolith. This regolith is of the order of 5 to 10 meter thickness. So this is a very fine-grained materials. If you look at the size, which is of the order of about 100 to 200 micron. So that's a very small size particle made up of impact glass, volcanic glass, agglutinates, also rock chips. So this is what fundamentally the astronauts collect from the landing site. So this is this regolith also underlined by mega regolith is also composed of the materials coming from different craters. Then you have a fracture crust. Even if you take a craters, for example, a fresh crater, which is just 3 million years old crater, this has thrown almost 2.5 lakhs ejecta boulders. Then you can see the left side, there are huge amount of boulder materials that thrown out of this crater. So these boulders are very important to understand the craters. From this studying these boulders, you can also estimate the impact velocity, impact, the size of the impactor, and so on. So this is how the boulders are distributed around the impact crater. The larger boulders are very close to the rim crater, and if you go away from, you will find a very smaller size craters, boulders. Then you can also study the shape of the boulders. That also gives lots of insight into the fragmentation process associated with the impact. So look, this Japanese, last year, the Japanese SLIM mission landed on the ejecta boulder field of a small crater called Shioli. They landed on the boulder fields. Therefore, the international missions gives very importance to these boulders because they gives lots of idea about the moon. Then comes to volcanoes. Like you find volcanoes on Earth, you also find volcanoes on the moon, but they are not active today. Most of the volcanoes formed between 4 billion years ago and up to almost 1 billion years. Between 4 and 1 billion years ago, most of the volcanic materials formed. The yellow patches are the volcanic lava flows, basaltic lava flows. We call it as mare. And you also find many volcanic glass beads in these basaltic materials because the Strombolian volcanic eruption that you find on Earth, this was very common on Moon. So the volcanic beads are basically come from the Strombolian volcanoes. You can see there are pictures of the volcanic lava flows, and these astronauts can go and sample these materials to study volcanism on the Moon. And look at the age of the moon, age of the volcanic material of the moon. They are varying from 4 billion years to 1 billion years. The different colors indicate the different ages of these lava flows. So astronauts can go and sample basaltic lava flows of different ages and bring the samples back and understand this volcanic process far better. Even when the volcanism occurs, it also produces a temporary atmosphere. Therefore, how the atmosphere forms from volcanic activity also an important science topic that can be dealt with. And even today, we discover many new volcanoes on the moon using the orbiter data sets. This was one study by us. And even some of the pyroclastic materials, which are possibly produced by explosive volcanic activity, they are also there sitting on top of volcanoes, which can be sampled. And look at, there are volcanic structures like you can say rills. These rills are like a rivers on Moon, but these rivers are, this is a flow of lava materials produce this type of structures. Even Apollo 15 landed near one of these rills and they collected some samples from them. So even volcanically active, even Moon is thought to be volcanically active. For example, this is one of the area called Aina structure, which is located on the near side of the Moon, which is thought to be volcanically active. And some signatures of gas release was found from these structures. Even NASA wants to land on this structure and study this recent activity. Of course, Indian astronauts also can explore this region. And there are lava tubes. So when the lava travels underneath in the subsurface, they produce like caves and tubes. Like, for example, you can see this is an example of lava tubes can be used to understand. And you can use this place to reside. Astronauts can go and live here on the surface of moon. Again, using the spectroscopic data sets, we have a very good data on the mineralogy of the entire moon lunar surface. For example, you have plagioclase, pyroxenes, olivine, and also ilmenite. These global mineral maps are available today. We can choose in an area where what type of minerals we want to collect can be done using these maps. Even geochemical maps, for example, titanium, iron, aluminum, magnesium, calcium, and also silicon. So these maps are also very useful to select the sites where we have to bring samples back to Earth. Even the geologic maps. This is also very important for sampling where to go on the lunar surface, where to collect the samples, what type of materials. The global geological maps are extremely useful to select the landing site. Therefore, it's not just we go to the moon and collect samples. So you have to study the whole global moon and come with the major scientific questions and prioritize your sample locations and land on the moon and collect them and bring them back. Even the tectonics, for example, moon also suffered some tectonics, for example, the subsidence. So when the lava flow forms, they also undergo subsidence during solidifications, due to which the structures like wrinkled ridges are produced. So this is, if you land very close to wrinkled ridges, we can understand how did they form. Moon also undergoes shrinking. So the global contraction also produced thrust faults on the surface of the moon. They are called lobate scarps. There are thousands of scarps are found, and these scarps also formed in the last 200 to 300 million years ago. Therefore, by understanding lobate scarps, we can understand the global contraction of the moon. They are also responsible for producing seismicity in moonquakes. So we also discovered such a lobate scarps using Chandrayaan-1 data from the crater called Schrodinger, and we can land here also. And here I come to geophysics. Here the astronauts installed a seismometer on the surface of the moon, and they recorded many moonquakes like deep moonquakes and shallow moonquakes, meteorite impacts, and also artificial impacts. So most of the observations are coming from here side. We don't have observation from the far side. So Indian astronauts can install many seismometers on the far side as well and understand the seismicity better. So far, we only know about 28 shallow moonquakes, which are comparable to earthquakes. And even our Chandrayaan-3 seismometer recorded one possible moonquake. So close to this standing site, even our group found many active faults. So these faults are possibly produced current seismic state. Even NASA wants to go and put seismometer on different parts of the moon. For example, the stars are the locations where they want to put the seismometer. Why? Because any moonquake structures, they pass through the interior of the moon and they are passed through core of the moon. Also, some of them are reflected by the core. So these reflected phases from the core can be recorded in different parts of the moon, like for example, Corollae crater, Shikar crater, and Chrysium and PKT. So here, using this experiment, by installing seismometers here, you can map the core of the moon much better, precisely. So we will know what is the size of the core. Also, the thickness of the upper shell of the moon crust can also be mapped precisely using seismology and also gravity. So this is one of the maps of crustal thickness map of the moon. And again, the heat flow. How much heat is flowing from the interior of the moon to the surface? So this also depending on the amount of radiogenic heat produced inside the moon. For example, thorium. Thorium is one of the radioactive isotope. It also generates huge amount of heat. So it is possible that if you go and study these areas which are rich in thorium, and you measure the heat, at the same time you measure outside the thorium anomaly region, you can measure the amount of heat coming from the interior of the moon much better. Magnetic field. Once upon a time, moon also had magnetic field very similar to that of Earth. The samples brought by Apollo astronauts back to Earth, they found the moon was having magnetic field at different times, even 4 billion years ago, 4.25 billion years ago to 2.5 billion years ago, even 1 billion years ago. Moon had some transient magnetosphere. So the magnetic sphere of Earth and also the moon, they also interacted with each other. We really don't know much about this process. So for example, the magnetic field of the Earth, moon was changed over a period of time. These models comes from the observations of the lunar samples. So the lunar samples provides lots of idea about the moon magnetic field. So this is also an important topic. This is another interesting topic, for example, boulder falls. So when an earthquake occurs in a hilly region, you have seen the boulders comes down, rolls down. So that type of observations were made on the surface of moon. There are hundreds of thousands of boulders roll down the slope of the moon, possibly due to moonquakes. So by mapping such a boulder falls, you can understand how the seismicity was in the past. Here, for example, these yellow dots are the region where huge amount of boulder falls occurred. And we can also date these boulder falls. And you see exactly Apollo 17 landed near a boulder fall site. For example, they went to a boulder which was rolled down. They brought this sample back to Earth and dated it. They found this boulder fall occurred about 27 million years ago, approximately. So similarly, based on boulder falls, we have found one crater in the south, near the South Polar region called Schrodinger Basin. We mapped all the boulder falls. We suggested this basin is very seismically active. Then now NASA wants to put a seismometer here. So this is the advantage. Even astronauts also can land on this basin. There's many scientific discoveries can be made. And this is one such a beautiful example in the Schrodinger Basin where you have boulder falls and active falls. This is where astronauts can also land. It's a very good place. Landslides. You know landslides, how catastrophic on Earth. Similarly, the landslides and gullies, debris flows also formed on the moon. This is also a very good topic. For example, the Apollo 17 also sampled one landslide materials from the moon. So landslides are also very interesting targets for study of the moon. Seismic hazard. Seismic hazard also very important. If you want to go and stay on the moon for a long time, our installations should not be affected by moonquakes. So we have to do seismic hazard map. Now we have a preliminary seismic hazard map prepared by our group for the South Polar region. Water is also important because the solar wind bombarded the moon and produced water. So this water also goes inside some of the materials in the moon. For example, these are impact glass beads. So they also, the solar wind implanted water also migrated inside these grains. The scientists brought the samples back to Earth and studied how water was produced. So this is another interesting experiment. Some of the volcanic beads which came from the eruption of volcanoes, they also contained some water inside. So this water comes from the interior of the moon. These materials also can be sampled by Indian astronauts. It's a very interesting topic. And water ice also present in the permanently shadow regions of the moon. And these are some of the permanent shadow regions of the moon, which are close to the South Pole. And if you look at the permanent shadow regions, you won't find ice on the surface. And this is one example, the image taken by shadow cam. They didn't find water on the surface, ice on the surface. But when collided with a rocket, one of the permanent shadow region was impacted by a rocket and it produced a plume. That plume also contained water inside. So this is how the water ice present in the permanent shadow region is proved by impact experiments. So this is why the volatiles, water ice are very important. They are present in the south polar region of the moon. We can understand the origin of this water, whether they came from asteroids, comets, or any other sources. This is why south polar region is very attractive. These are some of the missions went to the moon, and these are some of the missions going to the moon. And we need to have a long lunar base, Apollo. This is one of the picture given by NASA. This is how a lunar base in future, after 10, 20 years, we will be having this type of base. We can have one base like this, Indian lunar base. Can be established on the surface of the moon. We can establish some geological, geophysical observatory, even astronomical observatory. Even we can astrobiological observatory. Several things can be done. Even we can explore the outer part of the solar system. Even outer solar system also explored from here. So this is how we have to, yes, I am closing.
This is a reminder.
Yeah. So this is how we can have houses on the moon using 3D printer technology. Using the local materials called regolith boulders, we can construct houses like this. So this is where I am stopping my talk. And thank you very much for your patience in listening. There are huge amount of topics. There are wide range of topics are there. This is only a few samples that we have seen now. Probably I need several hours to elaborate all of them. Thank you so much.